look at the screen, while I change the voltage level, we see we have a width change for the output, and it will change until it becomes a straight DC. Alright, it's no more a square wave signal. Okay, so this is how the pulse width modulator is basically done. Electronic amplifiers are often symbolized by a simple triangle. They take in an input signal, amplify it, and use it to drive a load connected to its output. An operational amplifier, usually called an op-amp, is an amplifier characterized specially with two inputs: the non-inverting input, which is the positive pin, and the inverting input, which is the negative pin. And it's also specially characterized with a high gain. The operational amplifier basically amplifies the difference between the voltages at its two input pins by multiplying it by the gain. And so the output voltage is equal to the gain times the non-inverting input minus the inverting input. An example of an operational amplifier is the LM358. It's a dual op-amp, which means it has two operational amplifiers within it. In the diagram, one is labeled A and the other B. So for pin 1, we have outputs for operational amplifier A. For pin 2, we have the inverting input for operational amplifier A. For 3, we have the non-inverting input for A. Okay, for 7, we have the output for B, while 6 is the inverting input for B, and 5 the non-inverting input for B. And we have our power pins on pin 8 and 4. So to use the operational amplifier, we supply the amplifier with voltage on its power pins. Okay, so we have plus V, we have minus V, and we can supply between 5 to approximately 30 volts across that pin. Okay, and we then bring in the voltages whose difference we want it to amplify on the inverting pin and the non-inverting pin. Okay, so once we do that, the op-amp will respond on its V out. If the non-inverting pin is greater than the inverting pin, would have an output voltage given off, and that output voltage would be the product of the gain and the difference between V1 and V2. Alright, so for the LM358, from the datasheet, the open loop gain should be about 100,000. For example, if you have 20 millivolts on your non-inverting pin, the positive pin, and you have 10 millivolts on the inverting pin, of course we're going to have an output because the non-inverting is greater than the inverting. Alright, but then your output is not just going to be 10 millivolts, which is the difference between both. Your output is going to be multiplied by the gain. So the gain of this operational amplifier LM358 is 100,000. So you're going to have 100,000 times 10 millivolts, which gives a maximum of 1,000 volts. Okay, but because the op-amp doesn't have the supply of 1,000 volts, it will give out the maximum voltage it can give, okay, based on the power supply across its pins. The point for the operational amplifier, especially in the open loop configuration, is that any small difference in the input pin will make the output saturate, which means any little difference in the input pin will make the output give off its maximum possible voltage. The op-amp can be classified based on configuration into two types. We have the open loop op-amp and the closed loop op-amp. Of course, the open loop op-amp is without feedback, while the closed loop op-amp is with feedback. Okay, so I just talked about the open loop op-amp previously. In the open loop, we have the gain at its maximum being used. The op-amp operates with maximum gain. So for any little voltage difference, we have maximum output voltage given off. So what's the benefits of the open loop configuration? There's one basic benefit, and that's that they can be used as comparators. Okay, they can be used to make decisions Alright, so once a difference is noticed between the non-inverting and the inverting pin, and of course, if the non-inverting is greater than the inverting pin, an output will be given out. If the non-inverting is less than the inverting, you would have no output voltage on the output, or you have 0 volts on the output. Alright, so you could build a structure around this concept to help a circuit make certain decisions. Okay, so what kind of circuits can we make with the open loop op-amp configuration? We have circuits like the zero crossing detectors. Okay, so you want to know when a certain signal crosses the 0 volts. Okay, so when it crosses the 0 volts, you have an output or something, and maybe a microcontroller to detect that output voltage giving off, and then using that, of course, carry out a sequence of events. So that can be done with the operational amplifier. We have battery level sensing, we have threshold detection. Okay, then we have the pulse width modulated signals. Of course, pulse width modulation is done or can be done with the operational amplifier in the open loop configuration. Alright, so within a series of videos showing how these things can actually be done practically, basically practically, and then consequently in another video I'll be talking about closed loop op-amp configurations and how they can be beneficial to us as enthusiasts or actual circuit designers. Okay, so here I have my breadboard and components connected to it already. Here I have my op-amp. Alright, this is the LM358 Okay, I have these two resistors here of 51k ohms each, both dividing the voltage that will come from my power supply. Okay, so I have 10 volts coming from my power supply, and these resistors will be dividing that voltage by half. Okay, so that's why I have same value, and they would cause for 5 volts to be on the inverting pin, okay, which is the negative pin of the LM358, and on the positive pin, which is the next pin, I have it connected to the output of my variable resistor. Okay, and then one pin of the variable resistor is connected to my negative and the other pin is connected to my positive. Okay, so of course the positive is connected on this rail, negative is connected on this rail positive, the second rail here negative. All right, then we have, of course, this pin. This is the positive pin of the op-amp, and then we have the negative pin to be this last pin, which is connected to the negative from this jumper. Okay, then we have this resistor on the output leading to our LED. So first, to connect the probes of our oscilloscope. All right, so this first one goes to the inverting pin, and we have a second one at the non-inverting pin. So we can get to see what happens with both pins when our LED turns on. So we turn on our power supply, we see our LED is on, and that's because once you have the non-inverting pin higher than the inverting pin, we have our output saturate and we have our LED turn on. Okay, so when we say the output saturates, what we mean is that the output gives off its maximum possible voltage. Okay, it's just shooting out an output, and it's just like a switch, you turn on and turn off. Okay, so it saturates, it gives you the maximum possible voltage it can give. Okay, so when we turn this back down, all right, you see the LED turns off, so it's just coming on or going off, it's not in between. Okay, so in this case we are using the op-amp to compare two voltages. When the non-inverting input is higher than the inverting input, we have an output. When the non-inverting input is lower than the inverting input, we have no output. Okay, so here we have our circuit. All right, we have it's almost similar to what we had before. Okay, but for now we have a signal that will be coming from our signal generator, and we're going to place that on the inverting pin. So that will be coming into the inverting pin from this blue wire. Our signal generator probe is somewhere around there. It's coming in from this blue wire, and we have our DC supply of 10 volts coming into the, of course, the variable resistor connected to both the negative and the positive, okay, and then we're taking from the wiper here into the non-inverting pin. We'll see that if we turn on our power supply, okay, we see what the output is like. We have a square wave, of course, because remember we have the non-inverting signal to be a steady signal. All right, we're going to change its level with the variable resistor's wiper. Okay, so if we do that, if you look at the screen while I change the voltage level, we see we have a width change for the output, and it will change until it becomes a straight DC. All right, it's no more a square wave signal. Okay, so this is how the pulse width modulator is basically done. All right, so what's really happening here is if we take out the second channel's probe from the output and place it on we've placed the probe on our non-inverting pin. Okay, so we have both probes, one on the inverting pin and the other one on the non-inverting pin. Okay, so on the inverting pin we have our sawtooth waveform signal, while on the non-inverting pin we have our DC signal. Okay, and we can see that the level is 0 volts. Okay, so when we turn the knob, what happens is the voltage level changes and it increases. So the higher it goes, the width of the output changes, and that's because we are changing the point at which the output is triggered. Because when we had this at 0 volts, okay, we see that once the inverting signal is higher than non-inverting signal, we would have a low, we would have no output. But once the inverting signal is lower than the non-inverting signal, we would have a high output. So we had something like this. We had a high at this place, at this point, because this is the threshold at which the output is triggered. Because at this point, just below this point, is where the negative pin gets lower than the positive pin, and so would have an output voltage. We have that trigger of output on, and it stays on up to this point. Now if we move this, if we change the DC level to 1.29 volts, all right, that will mean we have a different pulse width, because previously we had our output turn on at this point and turn off at this point, but right now we're going to have our output turn on at this point and turn off at this point. So you see we have a wider width. Okay, so that's what actually happens. The voltage level changes, and as it changes, the threshold for our output signal changes.